On the edge of a quiet airfield outside Moscow, visitors can find a machine that looks less like an airplane and more like something left behind by another civilization. Its shape is unfamiliar, almost unsettling. A wide, flattened fuselage, twin tail booms, and proportions that defy everything most people think they know about flight. It sits silent now, weathered by time, stripped of its engines and purpose. Yet, half a century ago, this aircraft was meant to change the future of aviation and possibly the balance of power in the Cold War. This strange relic is the VVA-14, and behind it stood one of the most unusual figures in the history of aerospace engineering, Robert Ludwigovich Bartini. Bartini was not simply a Soviet aircraft designer. He was a mathematician, physicist, philosopher, and, according to many of his contemporaries, a man whose thinking was decades ahead of his era. Even within the secretive and highly competitive world of Soviet aviation design bureaus, Bartini stood apart. Colleagues described him as brilliant, difficult, and relentlessly theoretical. He was less interested in incremental improvements and more concerned with rewriting the fundamental rules of transportation. Robert Bartini was born in 1897 in the Austro-Hungarian Empire into a wealthy aristocratic family. His early life was shaped by privilege, classical education, and exposure to advanced European science. But the chaos of World War I and the Russian Revolution radically altered his path. Bartini embraced communist ideology, moved to the Soviet Union in the 1920s, and dedicated his life to engineering what he believed would be the transportation systems of the future. By the 1930s, Bartini was already recognized as an exceptional theorist. He worked alongside giants of Soviet aviation such as Andrei Tupolev and Sergei Korolev, but his career was far from smooth. Like many brilliant minds of his generation, Bartini became a victim of Stalin's purges. In 1938, he was arrested on fabricated charges and sent to a Sharashka, a secret prison laboratory where imprisoned scientists were forced to work for the state. Remarkably, even under these conditions, Bartini continued to develop advanced theoretical work on aerodynamics and aircraft design. It was during and after this period that Bartini began to question a basic assumption of modern transportation. Aircraft, ships, trains, every system, he argued, was optimized for only one environment. Ships were efficient but slow. Aircraft were fast but inefficient and fragile. Helicopters were flexible but limited in range and payload. Bartini believed this division was fundamentally wrong. Throughout the 1950s and early 1960s, Bartini undertook a systematic analysis of virtually every known form of transport. Using mathematics rather than intuition, he compared speed, energy efficiency, payload capacity, and operational flexibility. His conclusions were radical. According to Bartini's calculations, the most efficient mode of long-distance transport was not traditional flight at high altitude, but motion just above a surface, water, land, or ice, where the laws of aerodynamics changed dramatically. This phenomenon, known as ground effect, had been observed since the earliest days of aviation. Pilots noticed that aircraft flying very close to the ground seemed to float, requiring less power to stay airborne. Bartini took this idea further than anyone before him. In ground effect, air that would normally spill away from the wing is compressed between the aircraft and the surface below. This creates higher pressure, increased lift, and reduced drag. The result is an aircraft that can carry heavier loads using less fuel. Bartini realized something that few others did at the time. Unlike conventional airplanes, which must be as light as possible, ground effect machines could actually benefit from size and mass. Large surfaces meant more trapped air, more lift, and greater efficiency. In theory, this opened the door to aircraft of unprecedented scale and capability. By the early 1960s, Bartini was convinced that humanity had overlooked an entire category of flight. He envisioned vehicles that could skim just meters above the ocean at near jet speeds, combining the efficiency of ships with the speed of aircraft. But he did not stop there. Bartini wanted versatility, machines that could take off vertically, land anywhere, operate from water, snow, sand, or ice, and still fly like conventional airplanes when needed. In 1962, Bartini formalized these ideas into a revolutionary concept. He proposed an aircraft that would use vertical lift engines for takeoff and landing, then transition into high-speed ground effect flight for long-distance travel. At the time, vertical takeoff and landing, VTOL, was one of the most challenging problems in aerospace engineering. Experimental VTOL aircraft existed in both the United States and the Soviet Union, but they were inefficient, fuel-hungry, and mechanically complex. Bartini acknowledged these limitations. Lift jets consumed enormous amounts of fuel and added dead weight during cruise flight, but he believed ground effect could compensate for these drawbacks. By flying efficiently just above the surface, the aircraft could recover the energy losses of vertical operations. In Bartini's mind, this was not a compromise, it was a solution. What made Bartini truly unusual was his confidence in theory. While many designers relied on wind tunnel tests and on incremental prototypes, Bartini trusted mathematical models. He built scale models, conducted experiments, and refined equations that predicted performance far beyond what existing aircraft could achieve. To his supporters, he was a visionary. To his critics, he was a dreamer, detached from practical reality. Yet history would soon give Bartini an unexpected opportunity. In the early 1960s, the strategic balance of the Cold War was shifting. The United States Navy introduced a new generation of nuclear-powered ballistic missile submarines. Armed with Polaris missiles, these vessels could remain submerged for weeks and launch nuclear strikes from virtually anywhere in the world's oceans. For the Soviet Union, this represented a nightmare scenario. With more than 70,000 kilometers of coastline to defend, the Soviet Navy faced an impossible task. Traditional surface ships were too slow. Aircraft lacked the endurance to patrol vast ocean areas continuously. Somewhere within this strategic crisis, Bartini's radical ideas began to look less like science fiction and more like a potential answer. By the mid-1960s, the Soviet leadership took notice. And for Robert Bartini, the man who believed flight itself had taken a wrong turn, the moment had finally arrived to turn theory into reality. By the time Soviet officials began paying close attention to Robert Bartini's work, the Cold War had entered one of its most dangerous phases. The world's oceans, once seen primarily as barriers and trade routes, had become invisible battlefields. And beneath their surface, a quiet revolution was underway, one that fundamentally altered the strategic balance between East and West. In July 1960, the United States Navy conducted the first successful submerged launch of a Polaris ballistic missile from the nuclear submarine USS George Washington. For the first time in history, nuclear weapons could be hidden beneath the sea, mobile, virtually undetectable, and always ready. Unlike land-based missiles or bomber fleets, these submarines could not be easily tracked or destroyed in a preemptive strike. They represented a second strike capability that made traditional notions of deterrence obsolete. For American planners, this was a triumph. For the Soviet Union, it was a strategic shock. By the mid-1960s, US ballistic missile submarines were routinely patrolling the Atlantic and Pacific, some operating alarmingly close to Soviet territorial waters. These vessels could remain submerged for weeks or even months, limited only by crew endurance and food supplies. Nuclear propulsion made them fast, quiet, and independent of surface support. In the event of war, they could launch missiles with little warning, giving Soviet leadership only minutes to respond. The Soviet Navy simply did not have an effective answer. Conventional anti-submarine warfare relied on surface ships, maritime patrol aircraft, and fixed sonar arrays. But ships were slow and vulnerable, and the aircraft, though fast, were constrained by range, endurance, and the need for prepared runways. Patrolling tens of thousands of kilometers of coastline was not just difficult. It was mathematically impossible with existing forces. Soviet military analysts understood the implications all too well. Internal reports from the early 1960s described the submarine threat as persistent, unpredictable, and asymmetric. Unlike previous naval challenges, this one could not be solved by building more ships or aircraft of existing types. What was needed was something entirely different, an unconventional solution to an unconventional problem. It was in this context that Bartini's long-dismissed theories suddenly gained relevance. Bartini proposed an aircraft unlike anything then in service. It would not be confined to airfields or naval bases. Instead, it would operate directly from the sea itself, taking off from open water, flying long patrols at high speed just meters above the surface, and landing wherever conditions required. By exploiting ground effect, it could remain airborne far longer than conventional patrol aircraft, while still retaining the ability to climb to altitude when necessary. At the heart of Bartini's proposal was endurance. Anti-submarine warfare was not about speed alone. It was about time. Finding a submarine required long, methodical searches across vast areas of ocean. Bartini argued that an aircraft flying efficiently in ground effect could remain on station for hours longer than any existing platform, while carrying heavier sensor payloads and weapons. His design also emphasized flexibility. The aircraft would be amphibious, capable of landing on water, ice, snow, or marshland. It would not depend on the long concrete runways, which were vulnerable in wartime. In the remote regions of the Soviet Arctic and Far East, areas critical to submarine patrol routes, this capability was invaluable. Bartini envisioned a catamaran-like fuselage optimized for stability close to the surface. Twin hulls would help trap air beneath the aircraft, enhancing ground effect while providing buoyancy during water operations. Conventional wings would allow it to fly like a normal airplane when required, while vertical lift engines would enable takeoff and landing in confined or undeveloped areas. Most importantly, Bartini's aircraft would be equipped specifically for submarine hunting. It would carry magnetic anomaly detectors to sense disturbances in Earth's magnetic field, caused by submerged metal hulls. It would deploy sonobuoys and dipping sonar to listen for the faint acoustic signatures of enemy submarines, and it would be armed with torpedoes, depth charges, and naval mines, giving it the ability not just to detect but to destroy. To Soviet leadership, the appeal was obvious. Here was a single platform that could combine the roles of patrol aircraft, helicopter, and surface vessel, while operating in regions where none of those assets performed well. In internal discussions, the project was described as a potential force multiplier, a way to compensate for numerical and technological disadvantages through innovation. In 1966, after years of theoretical work and preliminary studies, the Soviet government formally approved development of Bartini's concept. The program was assigned a designation that reflected its ambitious scope, VVA-14, Vertical No Vzletaющая Amphibia, or Vertical Takeoff Amphibian, Project 14. Security surrounding the project was intense. Development was conducted under strict secrecy, with the aircraft officially registered as a civilian experimental vehicle. Early documentation avoided explicit military language, and prototypes were painted in neutral schemes to avoid attracting attention. Even within the Soviet aerospace community, few engineers were fully aware of the aircraft's intended role. For Bartini, the approval was a long-awaited vindication. Decades after being imprisoned by the very state he served, his ideas were now seen as critical to national survival. He threw himself into the project with renewed urgency, convinced that the VVA-14 was only the beginning. In his private notes from the late 1960s, Bartini wrote that the VVA-14 was a necessary step, not a final goal. He believed that once ground effect flight was fully mastered, it would lead to machines of unprecedented size. Transoceanic transports, floating air bases, even flying aircraft carriers. But first, the concept had to work in the real world. As the Cold War's silent struggle beneath the waves intensified, the fate of Bartini's radical aircraft became inseparable from the fate of the Soviet Union's ability to defend its shores. The VVA-14 was no longer just an experiment in aerodynamics. It was a response to one of the greatest strategic threats of the nuclear age. By the early 1970s, Bartini's idea had moved beyond paper and theory. In a guarded hangar far from public view, the VVA-14 was finally taking physical shape, and it was every bit as unconventional as the calculations that had given birth to it. Engineers who first saw the assembled airframe struggled to classify it. It did not look like a patrol aircraft, a seaplane, or a helicopter. Some remarked, half-jokingly, that it resembled a spacecraft that had landed by mistake on Earth. The VVA-14's appearance was the direct result of its mission. Its wide, flattened fuselage was designed to trap air beneath the aircraft during low-altitude flight, maximizing the benefits of ground effect. Twin tail booms extended rearward, supporting a high-mounted horizontal stabilizer that kept control surfaces clear of sea spray. The cockpit sat forward and high, giving the crew an unobstructed view during surface operations. Every line and contour reflected function over familiarity. Powering the aircraft in cruise were two Soloviev D-30 main bypass turbojet engines, similar in lineage to engines used on Soviet transport aircraft of the era. These engines gave the VVA-14 the ability to fly like a conventional airplane when required, reaching speeds of approximately 760 km per hour and climbing to altitudes of over 30,000 feet. This dual-mode capability was central to Bartini's philosophy. The aircraft would not be trapped in a single flight regime, but could adapt to changing tactical needs. But the most striking feature of the VVA-14 was hidden inside its fuselage. Bartini's original design called for 12 dedicated vertical lift engines, mounted in pairs and concealed behind doors in the upper fuselage. Each of these lift jets was intended to produce nearly 10,000 pounds of thrust. Together, they would allow the 57-ton aircraft to rise vertically from water, snow, or unprepared ground, something no aircraft of comparable size had ever achieved. If successful, the VVA-14 would become the largest VTOL aircraft in the world. This ambition came at a cost. Vertical lift engines added enormous complexity and weight, and during cruise flight they contributed nothing but dead mass. Western designers faced similar problems in VTOL programs such as the American 15-4 and the British Hawker Siddeley P-127, which would eventually lead to the Harrier. Bartini was acutely aware of these challenges. His answer, once again, was ground effect. By flying efficiently close to the surface, the VVA-14 could offset the inefficiencies of vertical takeoff in a way no pure VTOL aircraft could. Equally radical were the aircraft's amphibious systems. Instead of a traditional boat-like hull, Bartini designed inflatable pontoons mounted beneath the fuselage. These were divided into 12 sealed compartments and inflated using high-pressure air bled from the main engines. In theory, this allowed the aircraft to land on water with minimal structural weight, and then deflate the pontoons in flight to reduce drag. On paper, the solution was elegant. In practice, it would become one of the program's greatest engineering headaches. Inside the aircraft, the VVA-14 was designed for a crew of 3: pilot, co-pilot, and systems operator. Unlike earlier maritime patrol aircraft, which relied heavily on human observation, the VVA-14 was conceived as an electronically assisted hunter. Its system suite included inertial navigation, radar, and a search and aim system that could integrate data from multiple sensors simultaneously. For submarine detection, the aircraft was to carry magnetic anomaly detectors, long booms extending from the airframe that could sense minute disturbances in Earth's magnetic field caused by submerged steel hulls. It would also deploy sonobuoys, small expendable sensors dropped into the ocean to listen for propeller noise and machinery vibrations. In some mission profiles, the VVA-14 was intended to hover or fly slowly while using dipping sonar, a capability normally reserved for helicopters. Its weapons bay was designed to carry more than 2 tons of ordnance. This included anti-submarine torpedoes, depth charges, and naval mines. In theory, a single VVA-14 could patrol vast stretches of ocean, detect an enemy submarine, track it over time, and then attack, all without returning to base. Given the sensitivity of this capability, secrecy was paramount. Early prototypes were painted in civilian-style liveries and registered as experimental aircraft under the Aeroflot system. Official paperwork avoided references to anti-submarine warfare. Even flight test schedules were disguised as civilian research programs. This was not unusual in the Soviet Union, but the lengths taken to conceal the VVA-14's true purpose reflected how seriously the leadership regarded the project. The first prototype, known as Article 1M, was deliberately incomplete. It lacked the vertical lift engines, allowing engineers to focus on aerodynamics, stability, and water operations without the added complexity of VTOL systems. This staged approach was pragmatic and reflected Bartini's understanding that too many unknowns at once could doom the program. On September 4, 1972, the VVA-14 made its first flight. It did not rise vertically, nor did it skim the ocean at high speed. Instead, it took off conventionally from a runway, climbing steadily as test pilots evaluated its handling characteristics. Reports from these early flights were cautiously optimistic. The aircraft was stable, controllable, and responsive, an impressive achievement given its unconventional configuration. Subsequent tests focused on low-altitude flight. As the VVA-14 descended toward the surface, pilots observed a marked increase in lift and efficiency. The aircraft could sustain controlled flight in ground effect at heights of up to 8 meters above the water, far higher than many existing ekranoplan experiments. For Bartini, this was critical validation. His equations were no longer abstractions, they were being confirmed by reality. Encouraged by these results, Bartini continued to push forward. Throughout the late 1960s and early 1970s, he produced designs for even more ambitious ground effect machines. Some were civilian transports capable of crossing oceans with ship-like payloads. Others were military leviathans, enormous platforms that blurred the line between aircraft and naval vessels. In 1970, Bartini formally proposed one of his most audacious ideas to the Soviet Navy, a 5,000-ton ground-effect aircraft carrier. This colossal machine would skim across the ocean at speeds of up to 600 kilometers per hour, while carrying an air wing of up to 25 combat aircraft. It was, by any measure, an idea far beyond the technological limits of the time. Yet, to Bartini, it was not fantasy. It was the logical endpoint of a concept whose first real test was unfolding in the form of the VVA-14. But even as early flight tests hinted at extraordinary potential, cracks were beginning to form beneath the surface. The VVA-14 was an aircraft built on interdependent innovations. If even one of them failed, the entire concept would be compromised. And the most critical component of all, the vertical lift engines, had yet to arrive. The fate of the VVA-14 was decided not in the air, but in the unforgiving reality of engineering, bureaucracy, and time. By the mid-1970s, the aircraft stood at a crossroads, caught between extraordinary promise and mounting practical failure. What had begun as one of the boldest aviation experiments of the Cold War was slowly unraveling, piece by piece. At the center of the problem were the vertical lift engines, the very heart of Bartini's vision. Without them, the VVA-14 could never become the aircraft it was designed to be. Vertical takeoff and landing were not optional features. They were essential to the aircraft's ability to operate from remote coastlines, Arctic waters, and unprepared surfaces. And yet, from the beginning, the development of these engines had been plagued by delays. Responsibility for the lift engines had been assigned to a smaller, less experienced engine bureau already overwhelmed with other high-priority projects. The technical challenge was unprecedented. Each engine needed to produce enormous thrust while remaining compact, reliable, and lightweight. The Soviet Union had never built lift jets of this scale before. As months turned into years, prototypes failed to meet performance requirements, suffered from overheating, and consumed fuel at unsustainable rates. Bartini was deeply concerned. According to engineers who worked with him, he repeatedly warned that without reliable lift engines, the entire concept would collapse. Internal correspondence from the early 1970s reveals growing frustration. Test pilots could validate aerodynamics. Mathematicians could refine models, but no amount of theory could compensate for engines that simply did not exist. At the same time, other technical problems were accumulating. The inflatable pontoons, so elegant in concept, proved far more difficult to implement than anticipated. Designed to inflate and deflate in harsh maritime conditions, they relied on high-pressure air drawn from the main engines and distributed through a complex network of valves and seals. In testing, the system proved unreliable. Compartments leaked. Inflation times were inconsistent. In cold weather, materials stiffened and failed. Eventually, engineers made a painful decision. To allow testing to continue, the inflatable pontoons were removed and replaced with rigid metallic floats. This solution worked, but at a cost. The aircraft became heavier and less efficient, and one of Bartini's most innovative ideas was effectively abandoned. It was a compromise, and Bartini knew that compromises were eroding the integrity of the entire design. By 1974, the situation had grown dire. The lift engines were still nowhere near readiness. Without them, vertical takeoff from water, snow, or sand was impossible. The aircraft could no longer fulfill its defining mission. Bartini attempted to salvage the project through redesign. He proposed lengthening the fuselage and adding additional forward engines that would blow air beneath the aircraft during takeoff, creating an artificial cushion to assist water departures, something closer to a conventional seaplane assisted by ground effect. It was a desperate but ingenious attempt to preserve the concept. These modifications, however, introduced new problems: added weight, reduced payload, changes to airflow disrupted stability. Test results were inconclusive at best. The VVA-14 was becoming a machine burdened by layers of adaptation, each one moving it further away from the elegant theoretical solution Bartini had envisioned decades earlier. Then, in December 1974, Robert Bartini died at the age of 77. His death marked a turning point. Within the Soviet system, large experimental programs often depended on a single powerful advocate, someone willing to fight for resources, argue against cancellation, and absorb political risk. Bartini had been that advocate. Without him, the VVA-14 lost its champion. Shortly thereafter, the project was officially terminated. The Soviet leadership, facing economic constraints and shifting military priorities, chose a safer path. Instead of pursuing an unproven hybrid aircraft, they ordered the development of more conventional anti-submarine platforms. Aircraft such as the Beriev B-12 and later the Il-38, though less revolutionary, were familiar, reliable, and easier to integrate into existing doctrine. The age of radical experimentation gave way to pragmatic standardization. The VVA-14 never received its lift engines. It never entered operational service. Only a single incomplete prototype survived, eventually ending up abandoned and partially dismantled. An artifact of an alternate future that never arrived. Yet, to judge the VVA-14 solely by its failure would be to misunderstand its significance. Bartini's work influenced an entire generation of Soviet engineers. His theories on ground effect helped shape later ekranoplan programs, including the massive KM Caspian Sea Monster and the Lan-class missile-carrying ekranoplan. These machines, though different in form, embodied the same fundamental idea, that flight near the surface could unlock efficiencies impossible at altitude. Even more importantly, Bartini's intellectual legacy extended beyond any single aircraft. He believed that technology advanced not through caution but through bold leaps, through designs that forced engineers to confront the limits of physics and imagination. Many of his theoretical papers, declassified years after his death, reveal concepts that are still being explored today, from hybrid air-sea vehicles to ultra-heavy transports. In private writings, Bartini often spoke of time not as a straight line, but as a landscape. Ideas, he believed, did not belong to a single era. Some arrived too early, waiting decades for technology to catch up. He was convinced that ground-in-effect flight was such an idea. Perhaps his most haunting vision was the one that never left the drawing board, the 5,000-ton flying aircraft carrier, a machine that would skim across oceans at jet speeds, carrying fighters and bombers to any corner of the world. To modernize, the idea seems fantastical, but so did stealth aircraft, reusable rockets and nuclear submarines, until they became reality. Today, the VVA-14 sits silent, its paint faded, its purpose forgotten by most who pass it by. Yet it remains a monument, not to failure, but to ambition. It represents a moment in history when engineers dared to imagine entirely new forms of flight, driven by necessity, fear, and an unshakable belief in human ingenuity. In the end, Robert Bartini did not change the course of aviation in his lifetime, but he bent it, subtly, invisibly toward possibilities that others would explore long after he was gone. And in that quiet museum outside Moscow, the VVA-14 stands as proof that even unrealized ideas can leave a lasting mark on history.